Hello, hello, Mrs. Saunders here. Welcome to your first lesson in calculus. Today we've got two main questions we're going to answer. First of all, what is calculus? And two, what's a limit? Okay, maybe three questions. Here's a bonus. How do we find a limit? So what is calculus? A lot of times when a new math concept or a new science concept develops, it's because of an unanswered question or perhaps an unsolvable problem. Calculus developed from what seemed like unsolvable problems. For example, how do you find an instantaneous rate of change? Here's the graph of a parabola, and using 2 points, I can find the slope of a secant line anywhere on the graph. I can find the slope between D and A, between D and B, between D and C. But what if I want to know the slope of the graph of that parabola right at point C? It's only 1 point. More on that later. Another seemingly unsolvable problem was, how do you find the area under a curve? Here's a curve. And if you look under the curve, this thing, this shape that I'm coloring in right here, it's not a shape that we know or have a formula for as far as area is concerned. So if I want the area of that, what do? Well, I could approximate it using a rectangle. But the problem is I've got this stuff under the curve that's not accounted for. You see that? And then I've got this other section here that's accounted for but shouldn't be. So I could use a couple smaller rectangles. That helps a little bit. If I use even more rectangles, see, now we're getting somewhere. And even more rectangles. Now that's amazing. But can you ever find the exact area under the curve? So what is calculus? Calculus is the marriage of algebra and geometry. Calculus allows us to find exact answers to questions for which algebra and geometry could only provide approximations. Calculus has 4 big ideas. Limits, we're going to talk about those a bit today. What is the value of a function as you approach a value of x? Differentiation. What is the rate of change of an equation at an instant? I just showed you a bit of that. Integration. What's the area under the curve? And finally, series. How do we use polynomials to approximate transcendental functions? So much to learn. Here we go. Let's start with evaluating limits. So given this function, x cubed minus 1 over x minus 1, what characteristics would you expect the graph of f to have? Well, we have a fraction here, and we know that the bottom of a fraction can't equal 0. So we know that our graph can't exist at x equals 1. We also know something about the shape of the graph, because if you look at those leading terms right there, we've got x to the third over x. So that is x squared. Okay, so we have a graph with the power of 2, so like a parabola of sorts. There's what it looks like. It is indeed a parabola. But what do we do about the value of the graph at x equals 1? To get an idea of the behavior of the graph near x equals 1 without this graph in front of you, what we can do is use 2 sets of values. I'm going to make a table here, and I'm going to look at values of x approaching 1 from the left, and I'm going to look at values of x approaching 1 from the right. So you can see these values are getting closer and closer to 1 here, closer and closer to 1 from that direction. But the question I'm trying to figure out is, what's the graph doing? Where is the graph around x equals 1? So I'm just going to plug in each of these values into my function. Now, where do those values seem like they're headed? These 2.7, 2.9, 2.997. Looks like it's getting really close to 3. Now let's look from the right. So 1.1, I'm going to plug that into the function. 1.01, plug that into the function. Now look at these guys. Look at these values here. As we come from larger numbers to smaller numbers, what's happening to our function values? Again, the function is approaching 3. So what we'd say is the limit as x approaches 1 of the function is 3. Let's try another one. X can't equal 0 because that would give us a 0 on the bottom of a fraction. Now, without graphing it, what could I find out about the graph right around x equals 0? So again, we're going to plug in a bunch of values really close to 0. 1.99, 1.999, 1.9999. Okay, let's try the other side. Starting at 0.01, we've got 2.005, 2.0005, 2.0000, I've lost track. Lots of zeros and then a 5. So from the left, f of x is approaching 2. From the right, f of x is approaching 2. So if you do graph it, look right here. As we approach the x value of 0 from the left, and as we approach the x value of 0 from the right, the graph is getting closer and closer to 2. So we'd say the limit as x approaches 0 of our function equals 2. Let's talk about the actual definition of a limit. So the limit as x approaches c of f of x equals L. If the left side limit, the limit as x approaches c, look at this, that little minus sign, as x approaches c from the left equals L, and the right side limit, the limit of our function as x approaches c from the right, that's what that little plus sign is, equals L. So the first example we had, the limit of our function approached 3 from both the left and the right. And the second example we looked at, the graph approached 2 as x approached 0 from the left and from the right. So it's important to note that in order for a limit to exist at a value c, the one-sided limits, that is, from the left and from the right, the one-sided limits must approach the same value. Well, what if they don't approach the same value? There are times when a limit doesn't exist. Again, the standard limit, or a two-sided limit, only exists if the following are true. 1, both one-sided limits exist, and the one-sided limits are the same. So let's look at this graph here of the absolute value of x over x, and we're looking as x approaches 0. So if we look from the left, going this way, we're kind of following the graph, and looks like it's headed towards -1, yeah? But then as we look at the graph, as we follow the graph from the right, it's headed toward +1. So the limit as x approaches 0 from the left and the limit as x approaches 0 from the right, they don't match. Therefore, the limit as x approaches 0 of this function doesn't exist. Let's look at another one. The limit as x approaches 0 of sine 1 over x. Now this graph, it starts out okay, but then it gets to the middle and it just goes doing, 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 doing. And from the right, it starts okay, but then as it approaches the middle, it's just doing, 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 doing. It can't figure out where it wants to settle. This is called an oscillating function. So when does a limit not exist? Left and right sides don't match. The function increases or decreases without bound. It's like off to infinity or oscillation. So let's do some practice with this graph here. We're going to find first f of -2. So f of -2, that's just right there. That equals 2. Now, the next part says the limit as x approaches -2 from the left. So we're just going to trace the graph coming from the left. And where does it look like it's headed? It looks like it's headed to 2. Okay, now let's approach -2 from the right. We're approaching the x value of -2 from the right. Well, here's the graph, and these x values are coming this way. And as we're approaching -2 from the right, where's the graph headed? Well, whether or not it gets there doesn't matter, but the graph is headed towards 0. So 2 and 0, those are different numbers. The left side limit and the right side limit don't agree. So therefore, the limit as x approaches -2 of our function does not exist. Let's try 0. So f of 0, well, it's just a hole, okay? Doesn't exist. What about the limit as f of x approaches 0 from the left? So from the left, where's the graph headed? The graph is getting closer and closer and closer to 1. All right, what about as we approach 0 from the right, what's happening to the graph? The graph is getting closer and closer and closer to 1 again. So because 1 and 1 are the same number, the left and the right limits both agree, then we can say that the limit as x approaches 0 of f of x equals 1. Never actually gets to 1, but that's where it's headed. Let's try an x value of 1. What's f of 1? F of 1 is nowhere on there. It doesn't exist. What about the limit as x approaches 1 from the left? So we're following the graph here. Oh, look where we're going. Whoa! Falling off a cliff. We're going to -infinity. As x approaches 1 from the right, positive infinity. Does -infinity equal positive infinity? It does not. So the limit as x approaches 1 does not exist. What about the x value of 2? What is f of 2? Well, it's kind of hanging out down here, isn't it? F of 2 is -1. The limit as x approaches 2 from the left, we're just following the graph of those x values, and the graph is getting closer and closer to 1. If we come from the right, the graph is getting closer and closer to 1 again. All right, so we have matching left and right side limits. So the limit as x approaches 2 of this graph is 1. Last one, let's look at f of 4. All right, f of 4 is down here. It's -2. The limit as x approaches 4 from the left, so we're just following the graph to see what happens as we get closer and closer to an x value of 4. And looks like we're headed towards 0. And then from the right, following the graph from the right, that one's headed towards -2. Left limit and right limit don't agree. Therefore, the limit as x approaches 4 of this function does not exist. All right, that was your first lesson in calculus. It only gets better from here. Thanks for being here.